Continuing on with class number 8, here's some additional examples from Cengel. There's some of these are short. This is short, so I'm going to combine a bunch of them. A bunch? I don't know about a bunch. I have these first ones way too. This is just like the most recent example that in the previous video, where we have a rigid tank. See, there's the magic word, rigid, that contains 500 kilopascals of air at 150 degrees Celsius. And when there's some heat transfer surrounding it, the temperature and the pressure inside the tank drop to 65 degrees Celsius and 400 kilopascals respectively. Determine the boundary work done during this process. There's that phrase, boundary work. Well, this is a trick question because, and we already see the graph right here. We can't get an area underneath there, like maybe there's a little shadow right underneath there. There's no work. There can't be any work, right? Because work, that as we defined it, is pressure times change in volume. But dV is equal to 0. There is no delta V in here. Therefore, the work from 1 to 2 is equal to 0. No work takes place. There could be heat transfer that's taking place, but no work. So this is an isometric. Isometric, there's another name for it. I can't remember it offhand. Process. And that's not unheard of, to have that type of a process. Or to model something as that type of a process. That's probably more of an important phrase to say for your constant volume processes. All right, so now we take a look at boundary work from a constant pressure process. That was a constant volume. Now we have a constant pressure, which is also known as isobaric. Good thing to know. So the pressure remains constant throughout the thing. So a frictionless piston, so we don't have any losses going on here. And we have 10 pounds of steam at 60 psi and 320 degrees Fahrenheit. Heat is now transferred to the steam until the temperature reaches 400 degrees Fahrenheit. If the piston is not attached to a shaft, okay, there's nothing right there that's attached, so nothing can take it away, and its mass is constant. Determine the work done by the steam during the process, right? So we're placing heat into here, but the steam is doing work. We want to find what that is. We will look this up soon with something called enthalpy. I believe that's true. I think we could get the same result, but we'll see later on. Maybe not. I'm trying to think about that. I'm tired. Let me let's take a look at these different conditions right here. So at state 1, we have a pressure is 60 psia, and the temperature is 320 degrees Fahrenheit. And then at state 2, the pressure is 60 degrees psia, and so this is 1 and 1, and this is 2 and T2. We have 400. So and they said it was steam. So let's look that up in our book. This comes out of a different book, but let me look it up here. All right, so we would be in the English units and be into, I think it's F7 first. Let's always check. We are at I think I only have, we don't have the pressure indexed saturated table. So all we can do is look for the temperature of 320. So at 320 degrees, we have a pressure, saturation pressure, let's look it up on there, boom, of 89.609 psia. That means what we need to do, that pressure is higher than our pressure. We have 60 psia, so it must be superheated steam. You can also check it by just going to the superheated steam and going to 60 psi. That was nice of them, right? Right there, boom, 60 psi. And here's our 320 degrees. That's our first state. So we have a specific volume of one. At state 1, it's 7.485. And these are cubic feet per pound mass. Let's go up to the top and double check that. Yep, cubic feet per pound mass. Boom. And then at state 2, we're at 60 still, but now we went up to 400 degrees. And we have a specific volume of 8.353 cubic feet. Oops, you can't see my hands here. Oh, there, cubic feet per pound mass. All right. So, so we look those up, and we're in a constant pressure process. So the work between states 1 and 2 is going to be equal integral P dV from 1 to 2. But the pressure is constant, so that could go to the outside. And so what we end up having is P1 or P2 times V2 minus V1. But we don't have V, we have specific volume. So what we could actually write is P1 V2 minus V1 times mass. And they told us that it was 10 pounds mass right in there, right? So these are cubic feet per pound mass, and then we multiply by the pound mass. We have to be careful here because this is in PSIA. These are in cubic feet. We need to turn them into one or the other. I choose to go with feet, better, especially because we're going to need to use a conversion factor. They didn't tell us this, but they wanted the answer in BTUs. And remember that we have this number 778. I never put a thing at the end of this, but I think they said 1.7 is cubic feet or feet per foot pound force over BTU. This phone never rings, and I am not answering it. It says Directory Assistance in Nevada. I don't know how that phone number got onto a call log. Somebody probably hates me, and they stuck my name on the thing. That's because nobody ever calls that phone, and I don't answer it. They can. I've answered it once or twice. Anyway, okay, so here's 60 psi. Maybe I should put the units out here. Pounds per square inch. Go 144, and that's inches squared per foot squared, right? So that's just 12 by 12. I'll put the mass over here. It's going to be 10 pounds mass. And then here we're going to have 8.353. I guess I can write over here. Okay. 7.485. And remember, those were cubic feet per pound mass. So we got rid of our pound mass. And there's feet squared in here in the denominator. So we're getting rid of those, and we're really getting rid of that right there. So we're going to have pounds feet. And so I got 75,000. That's interesting. Pounds force. And you can go ahead and divide by 778.17, although I didn't actually put the 17 in there, so don't call me a liar, just lazy. So we're going to say that our work between 1 and 2 is going to be 96.40 BTUs. And we haven't been really using much BTUs, but we will be. Want to kind of give a nod to the old ways. All right, so I'm going to put the next 2 examples on the next video. What do you say? Sure, why not? It's only 8:15 on a Monday evening.